Fundamentally, limits are promises. When I tell you the limit of f of x equals L as x approaches a, I'm promising you something. I'm promising you that I can get f of x as close to L as you like, as long as x is close enough to a. Now, thinking of limits as promises helps us to understand statements like these. Let's suppose that you tell me that you know the limit of f of x as x approaches a is equal to something. Maybe this is equal to L. And maybe the limit of g of x as x approaches a is equal to m. Well, what that really is a promise that you can make f of x as close to L as I like. And it's a promise that you can make g of x as close to m as I like, as long as I'm willing to make x close enough to a. But if you can promise me that you can make f of x close to L and g of x close to m, then I can turn back and promise you that f of x plus g of x is as close to L plus m as you like. Right? If I want to make this close to something, I just ask you to make f of x close enough to L and g of x close enough to m so that f of x plus g of x is as close as you like to L plus m. In other words, the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limits, and the limit of a product is the product of the limits. And what about quotients? And something similar is true for division. If the limit of f of x as x approaches a is L, and the limit of g of x as x approaches a is m, which isn't 0, then the limit of f of x over g of x as x approaches a is L over m. In other words, the limit of the quotient is the quotient of the limits, provided those limits exist and the limit of the denominator is non-zero. Now let's do something with our newfound knowledge about limits of quotients. Here's a limit problem. I want to know the limit of x squared over x plus 1 as x approaches 2. Right? I want to be able to promise you that x squared over x plus 1 is close to something whenever x is close enough to 2. This is the limit of a quotient. And the limit of the quotient is the quotient of the limits, provided the limit of the denominator is not 0. And in this case, it's not. So the limit of the quotient is the quotient of the limits. Here's the limit of the numerator. The limit as x approaches 2 of x plus 1. This is the limit of the denominator. Now, this is the limit of x squared. X squared is x times x. This is the limit of a product. And the limit of a product is the product of the limits. So I can replace the limit of the numerator with the limit of x as x approaches 2 times the limit of x as x approaches 2. Because this is the limit of x times x. And here is the product of the limits. The limit of x times the limit of x as x approaches 2. The denominator here is the limit of x plus 1 as x approaches 2. But that's a limit of a sum. And the limit of the sum is the sum of the limits. So the limit of x plus 1 is the limit of x plus the limit of 1 as x approaches 2. Let's keep going. So I've got the limit of x times the limit of x over the limit of x plus the limit of 1, and all of these limits are being taken as x approaches 2. What's the limit of x? That's asking, what can you guarantee x is close to if you're willing to have x be close enough to 2? 2 is the limit of x as x goes to 2. So the limit of x as x goes to 2 is 2. The limit of x as x goes to 2 is 2. This dot is for multiplying. Divided by the limit of x as x approaches 2 plus, what's the limit of 1 as x approaches 2? This is asking, what can I guarantee 1 is close to if I'm willing to have x be close enough to 2? Well, 1 is already close to 1. Right? The limit of a constant is that constant. So this is just 1. 2 times 2 is 4. 2 plus 1 is 3. And so the limit of this expression is 4/3. At this point, you're asking yourself, why is the rule for limits of quotients different than limits of products? A limit of a product is the product of the limits, as long as the limits exist. Why do I have to worry about the limit of the denominator being non-zero when I'm taking a limit of a quotient? Most basically, the problem is that you can't divide by 0. You can't go around telling people that the limit of a quotient is a quotient of the limits, because the limit of the denominator might be 0, and then you'd be telling people to divide by 0, which they can't do. You can't divide by 0. But you can think about it even, let me a little bit more subtly. Let's kind of unpack this a bit. Here's an example to think about. The limit of x over x minus 3 as x approaches 6. This is no problem, right? The numerator is a number close to 6, that's how we're thinking about it, and the denominator is a number close to 6 minus 3. A number close to 6 minus 3, that means the denominator is a number close to 3. I've got a number close to 6 divided by a number close to 3. Well, that's a number close to 2. And indeed, I mean, this limit is equal to 2. I can make this quotient as close to 2 as I like, because I can make the numerator as close to 6 as I need, and the denominator as close to 3 as I need to guarantee that this ratio is as close to 2 as you like. So that limit is 2. But what if, instead of asking about the limit as x approaches 6, I'd asked about the limit as x approaches 3? Well, then what would I know? Then I'd know that the numerator was a number close to 3, and the denominator was a number close to 3 minus 3. The denominator is a number close to 0. The limit of the denominator is 0. That's exactly the scenario that the rule for taking limits of quotients is forbidding us from considering. We're not allowed to use the rule for limits of quotients here because the limit of the denominator is 0. But what really goes wrong? I mean, yeah, I can't divide by 0. Fine, I'm not going to divide by 0. I'm just dividing by numbers close to 0. But what happens when I divide by numbers close to 0? A number close to 3 divided by a number close to 0, is that close to anything? If a number is close to 0, it might be positive and very small. 3 divided by a small positive number is a huge positive number. What if the denominator were a number close to 0 but negative? Very small negative number close to 0. 3 divided by a small but negative number, that would be a hugely negative number, very negative. Well, this means that this thing should be getting close to both a gigantic positive number and a very, very negative number. This thing isn't getting close to anything. Fundamentally, that's the problem. But not all is lost. Think about this slightly harder example. The limit of x squared minus 1 over x minus 1 as x approaches 1. It's a limit of a quotient. So your first temptation is to replace the limit of a quotient by the quotient of the limits. But you can't replace this with a quotient of limits because the limit of the denominator is 0. The limit of x minus 1 as x approaches 1 is equal to 0. So it seems like our limit laws have failed us. And we've got one more trick up our sleeve. Look at the numerator. X squared minus 1, that factors as x plus 1 times x minus 1. So let's record that fact. I'm going to record the fact that the numerator factors as x plus 1 times x minus 1. Now I've still got a limit of a quotient, and the limit of the denominator is still 0. So it seems like we're stuck. But now I've got a factor of x minus 1 in the numerator and a factor of x minus 1 in the denominator. And I can use that fact. What I want to do is imagine canceling these. Right? I'd like to write that this is equal to the limit of just x plus 1 as x goes to 1. But note, these are not actually the same function. Right? This thing up here is not defined at 1. This thing is defined at 1. And yet the limit doesn't care. The limit only depends upon values of the function near 1. And near 1, this and this are exactly the same. I'm not allowed to plug 1 into this. I am allowed to plug 1 into this. They're different functions. But those functions are equal if you're only considering values that are near and not equal to 1. As a result, these limits are the same. This is now the limit of a sum, and the limit of a sum is the sum of the limits. So this is the limit of x plus the limit of 1 as x approaches 1. The limit of x as x approaches 1 is 1. The limit of 1 is a constant as x approaches 1 is 1. This is 1 plus 1. This is 2. And so that limit is equal to 2. And our limit laws have again saved the day.